Hi everyone, today we are going to build a simple yet still challenging JavaScript project. We are going to be building an audio visualizer. You might have seen audio visualizers in different music players or while listening to a song on YouTube. So we are going to take a piece of audio and visualize it with the help of JavaScript, specifically using the Canvas API and the Web Audio API. This project is actually part of my JavaScript mastery course. I just want to quickly plug in that the early bird offer for batch 2 is currently going on. If you're interested, you can check out this video or visit the link in the description box below. Without wasting any more time, let's get to coding. In this video, we are going to be building an audio visualizer, something like this that you're seeing on the screen. But before we jump into coding, I want to walk you through the approach first. Let's take a look at the high level approach that we are going to be taking in order to build this project. Step number one would be to set up the project files themselves. So this is a vanilla JavaScript project and this is a web-based project. So we'll be requiring an HTML file and we'll be using a JavaScript file. We won't be styling it too much, just some basic styles, which we'll be putting into the head section of our HTML file itself. So that's why we won't be creating a separate style sheet. So inside of our HTML, we have two main elements. First is the input element that will be used to fetch a piece of audio file from the user. So whatever audio the user wants to visualize, he or she will be uploading it with the help of this input tag or this input element. And then we'll be processing this audio programmatically with the help of the Web Audio API. Now, after processing this audio, we need to visualize this audio, for which we'll be using the Canvas element and again the complementary Canvas API for actually drawing stuff onto this canvas. This HTML file will link to a JavaScript file, which will contain all of the related logic that makes use of the before mentioned APIs. Now that we know the basic structure of the project, let's talk about how you would process this audio data. So an audio file is a file. When a user uploads it, it is a type of a file. So this audio file, let's say this is an MP3 file. In order to visualize it, we need to convert it into some piece of data. For example, in our case, we'll be converting this file, this audio file, into an array of data so that we are able to plot this into a graph. Step 3 is to visualize. Now that we have this array of data in terms of numbers, we'll then be using this array to plot a chart with the help of the Canvas API. Now, step number 4 is to set up a visualization loop, which means that we have an audio file and we convert that audio file into data and then that data is plotted into a bar chart. But we don't just want one static bar chart. We want it to be such that when the music is playing in real time, we are getting different data from this audio and that data is plotted continuously and a new graph is created so that we get that actual visualization effect so that we can feel that the graph is actually moving up and down. So we need to set up a loop such that the audio is continuously converted into some real-time data and that data is continuously plotted onto the bar chart. All right, now that we understand the high-level approach, now let's get to coding. All right, so let's get to coding. Step number 1 is to set up the project files. So here I have my VS Code opened up and as I said previously, we just need an HTML file and a JavaScript file. Let's start with the basic structure of an HTML file. So I have a basic HTML template here, the HTML tag, the head tag, and an empty body for now. Head tag has a couple of meta tags and the title. Let's add a style tag as well. And let's leave it empty for now. I mentioned previously that we'll be making use of two tags specifically. First one is the input tag to get an audio file as the input and the canvas tag. So let's add them here. Input canvas. By default, the input tag in HTML takes the type of a text input, but we want to accept a file and specifically an audio file. So audio, let's give it an ID as well so that it's easier when we are trying to manipulate the DOM. So we'll make use of this ID when we want to fetch this audio file from the DOM. And for the canvas tag as well, let's give it an ID. Say, let's just call it canvas. Let's add some styles to this canvas. This is probably the only element on which I'll be adding the styles to. Let's make the height 800 pixels for now. We'll see how it looks like later on. Let's give it a display block as well so that this canvas element appears as a block element and it does not appear next to this input element on the screen. I want it to be on the next line. Lastly, let's also link our JavaScript file. So our JavaScript file is empty for now. Let's link it. So this index.js is empty for now. Paste this script tag at the bottom of my body instead of placing it inside of the head to make sure that the content of the body loads first and only after that our script is loaded, because a script is dependent on these two elements existing. So just to ensure that the DOM is loaded before the script is actually executed, I've placed it inside of the body and at the bottom of the body tag. Now let's see how our web page is looking like inside of the browser. So here you go. So I have this button that lets me choose a file. I'm going to be using a copyright-free music over here. All right, open. So right now, selecting this audio file does nothing because I have not added any logic yet. So to be able to do something so that whenever the user adds a file, we need to make use of event listeners. So I need to attach an event listener on the change event of this input here. In order to set an event listener on the input element, I need to first fetch that element from the DOM. To get an element from the DOM so that you can manipulate it, you can add event listeners to it, you make use of the get element by ID method on the document. So document dot get element by ID. And remember the ID that we set was audio. So I'm going to use audio and this will give me the input element here. So we can check that by doing this. So dot log input element. So let's test whatever we have written so far is working fine. I'm going to attach this song. And as you can see in the console, we have this input element here. So this input element variable now holds the actual element from our web page. So to add an event listener onto this input element, we'll be making use of the add event listener method. So onto the element, we'll attach an event listener with the help of this method. So we don't want to do anything with this input element. So I'm not going to store it inside of a variable. All I want to do is add an event listener on the change event here. So this change event, as you can see, console.log. So this adds an event listener. So basically, whenever a change happens to this input element, then this callback function will be executed. And this callback function will be provided the event object itself. So inside of this callback function, I've simply just printed the event object. So let's see how this event object looks like and refresh. So this is a change event. So whenever I change the input value, which is when I upload a file. So now as you can see, this event is printed. And these are all of the different properties that this has. And as you can see, the type of this event is change. So here we have a target property here. And inside of this target property, we have a files property that actually stores the file that we have uploaded. So let's access this file with the help of this event object. Const file equals to event.target.file0. Let me show you this file object as well. So as you can see, now we have access to the file that was just uploaded by the user here. Now that we have the audio file, we want to process this audio file and convert it into some usable data. So we have an MP3 file, we want to convert it into an array buffer. In order to convert it into an array, we will make use of something known as file reader. So this file reader will read this file and then convert this MP3 file into an array buffer. You already know what arrays are in JavaScript. Arrays are a collection or a list of data. Array buffer is also an array, but it is a special type of array. An array buffer is useful for handling raw binary data. So this MP3 file will be converted into raw binary data that will be stored inside of this array buffer. This array buffer data structures makes it more efficient to work with raw binary data. You can learn more about array buffers using the link that I've provided. So let's remove this console statement. So to create a file reader, we make use of this syntax, this constructor function. So this creates a new instance of the file reader class. So to read this file, we make use of the read as array buffer method on this reader, and we provided this file. So now this read as array buffer method will read this audio file and then create a new array buffer from it. But this read as array buffer method is an asynchronous method. It does not return anything directly from this. So you cannot do something like this, array buffer. Let's see what the value of array buffer here would be like. It does not return an array buffer. As you can see, it does not return anything directly from it. It is an asynchronous operation. So in order to actually get the return value, we make use of event listeners again. So we will attach a new event listener on this reader using the add event listener method on the load event. So this load event will be triggered as soon as this file is read as an array buffer. And then this callback function will be called whenever this operation is completed. So let's see what is the value that will be passed to this callback function. So this is the event here, and this is the target, and this is the result. So this property here under the target property actually contains the array buffer. Array buffer equals to event.target result. Now that we have this array buffer, we still can't quite use it to visualize it into a bar chart. So we further need to process it more. Now we need to convert this array buffer into an audio buffer. So this array buffer will be converted into an audio buffer with the help of something known as the audio context provided by the Web Audio API. So just like how you created a reader using the file new file reader syntax, similarly, we'll create a new audio context with the help of this new keyword here. So new. So here notice that I've not directly called this audio context function here. Instead, I have called it like this, window.audio context or window.webkit audio context. And I've used the OR operator here. So we are using this OR syntax and we have provided it two values to make sure that either of them at least exists. If window.audio.context exists, then this OR operator will return the LHS from this expression here, and then this new operator will create an instance of window.audioContext. Otherwise, if it does not exist, the RHS will be returned. So window.webkit will be returned, and then this new operator will create a new instance of window.webkit So in most modern browsers, this value will exist. But for compatibility reasons, we are checking it first if it does not exist, which is in the case of older browsers or legacy browsers. This will then default to WebKit audio context. Now we can use this audio context to convert this array buffer into an audio buffer. So to do that, we make use of the decode audio data method on the audio context. Decode audio data. So this decode audio data method takes the array buffer as an input and a callback function. So this callback function will be triggered or executed as soon as this array buffer is converted into an audio buffer. And then this callback function will be provided the audio buffer as an argument. So let's check how this audio buffer will look like. So as you can see, this was converted into an audio buffer, and this is how this audio buffer data object actually looks like. It has a duration property, a length property, number of channels, and a sample rate. Now we can actually use this audio buffer to visualize the audio data. Now, in order to visualize this audio buffer, we need to first understand these properties a little bit because we're going to be plotting these properties into a graph. So we need to understand what property is useful for us when we want to plot it into some sort of visualization or into some sort of a chart. First, let's take a look at what channels are. You've worked with any sort of audio editing applications, then you might have at least some idea of what channels are. Channels refer to the independent audio signals contained within an audio buffer. So each channel represents a separate stream of audio data. Common examples include mono, which means a single channel. So if the number of channels is one, then it is also referred to as mono. Another common example is stereo, which contains two channels. For example, inside of your laptops, if you have a left and a right speaker, they become two channels, left and right audio streams. One more example is surround sound, in which you have multiple different channels to give you that experience. For example, a 5.1 surround sound system has six channels. So there are six streams of audio, and sometimes you might have experienced when you're listening to music on headphones. Again, you have two channels in a headphone. The music that you hear out of it is in such a manner that it travels from the left channel to the right channel, or from the right channel to the left, which you can think of it as that these two channels have separate streams of audio. Sometimes these are exactly the same, sometimes they are a little bit different to give you that traveling music effect. Same with the surround sound system as well. So here in our audio, we have two channels, a left and a right channel. Next thing that we need to talk about is the sample rate. So as you can see, our audio buffer has a sample rate of 44,100. So the sample rate is the number of samples of audio carried per second measured in hertz. For example, if the sample rate is 44,100, you can say that the sample rate of this audio is 44.1 kilohertz. So this just means that there are 44,100 samples of audio per second. So this sample rate determines the quality of the audio. The higher the sample rate, meaning there are more samples per second of this audio, which means that the quality of the audio is also higher. If you reduce the sample rate, then the quality of the audio also reduces because we have lesser samples per second of the audio. So we'll be using this channels property and this sample rate property to visualize our audio file. Let me remove this console statement and let's create a new function here for visualizing, and this will accept an audio buffer. So after converting this array buffer into an audio buffer, we call this visualize function and provided the audio buffer, and this visualize function will be responsible for visualizing this audio buffer or drawing onto the canvas. We first need to get the canvas element from the DOM in order to draw on it. So again, we'll make use of the get element by ID method. Const canvas equals to document.getElementById, and since we set the ID of the canvas as canvas only, so we'll provide it the string canvas as an argument, and then let's print this to see if we were successfully able to get this canvas element or not. So as you can see, we now have access to this canvas element. Now, in order to draw something onto the canvas, we need a context. Just like we had an audio context, we also need a canvas context. And since our bar chart is only two-dimensional, we'll provide it 2D as an argument. So canvas.getContext. This method will return a canvas context, which will be then used to draw something onto this canvas. Now all we need is the actual data that we'll be plotting as a bar graph. So right now we have two streams of data since we have two channels, the left and the right channel. So we can either plot two bar graphs here for the left and the right channel, or we can just plot one bar graph here. So let's start with just one channel. In order to get the channel data, you make use of the get channel data method on the audio buffer. So const channel data equals to audio buffer get channel data. We've provided 0 as an argument, so this will return the channel data of the first channel. So let's see what this value holds actually by logging it onto the console. This is the channel data, and as you can see, this data is a float 32 array. So this is an array of floats. Now let's understand what this array actually means. Like, what is the meaning behind these different numbers here? So the audio buffers get channel data method runs a float 32 array containing the PCM data associated with the channel. So when we did audio buffer.get channel data 0, it returns the PCM data associated with the first channel. Now, what is meant by PCM? So PCM stands for pulse code modulation, and it is a method used to digitally represent analog signals. When you hear music, that is an audio signal, and when we work with it in computers, we want to convert this analog data into digital data, and for that we use a method known as pulse code modulation. PCM is a fundamental concept in digital audio and is widely used in various audio storage and transmission formats, including CDs, digital audio tapes, and computer audio files. So, here are some key concepts of PCM data: analog to digital conversion. So, we learned about the sample rate previously. The analog audio signal is sampled at regular intervals. The sample rate, example 44.1 kilohertz, determines how many times per second the signal is sampled. So there are 44,100 samples per second in an audio that has this sample rate. Quantization: each sample is then quantized, meaning it is assigned a numerical value that represents the signal's amplitude at that specific point in time. Digital representation: the result of this process is a series of numerical values which are stored in a digital format. These values represent the amplitude of the audio signal at each sampling point. So if our audio has a sample rate of 44.1 kilohertz, which means that in every second of that audio, there are 44,100 samples. And in each of these samples, at every point, whenever it is sampled, that signal is quantified. So a number is attached to it, and that number represents the amplitude of that signal. So if the sample rate is 44.1 kilohertz, which is 44,100 samples per second, the number of values in the channel data of an audio buffer depends on the duration of the audio, not just the sample rate alone. The sample rate tells you how many samples there are per second, but the total number of samples, that is the length of the channel data array, is determined by the sample rate multiplied by the duration of the audio. For example, if the duration of the audio is 5 seconds and the sample rate is 44.1 kilohertz, this means that the total number of samples there will be 44,100 samples per second into 5 seconds. So this comes out to be 220,500 samples. This means that the channel of the audio buffer will contain 220,500 values. So in our case, the audio buffer's duration is 120 point something, and the sample rate is 44,100. So if I multiply the exact duration by the sample rate, then it comes out to be 5307265, 5307265. So this array contains the PCM data, which is the amplitudes of the signals whenever the signals are sampled inside of this array. So amplitude is the strength of that signal at that point, or the magnitude of that signal in terms of an audio file. Amplitude can also be thought of as the loudness or the volume of that signal at a certain point. So we'll be using this amplitude data to plot a bar graph. All right, so our audio buffer array over here has around 5 million items or 5 million data points, and plotting these data points onto a graph is a tricky thing. The width of our canvas is about this long, and if I close this developer tools panel, then maybe a little bit longer than that. So instead of plotting each and every item from our audio buffer array, what I'm going to do is divide the array into chunks or divide the array into separate parts. For example, this array has been divided into 6 different parts. And after dividing our array into some chunks, some X number of chunks, each chunk will be processed so that only one value is represented from that chunk. So here I have 6 chunks in this example, and each chunk is represented by one single data point. So eventually, instead of plotting each and every data point, we are only going to plot one data point from each chunk. Thus, our entire data set or the length of our data set will be reduced. Next, we want to know how many chunks that we want. So number of chunks, this can be any value that you want it to be. I am setting it to 100 because I feel like 100 is a good data point. 100 is a good number that will look good on the canvas. We'll see how it looks like and then adjust it accordingly. Then we'll find out the chunk size. The chunk size is going to be channel data dot length divided by the number of chunks. Let's round this number up to an integer. Now let's create a loop starting from 0 till the number of chunks. Now let's determine the chunk itself. So we are going to create a chunk using the slice method. So the slice method slices an array or cuts a part of an array and returns a new array out of it. So this is the starting index. The starting index is going to be the index multiplied by the chunk size. So this is the end index, the starting index and the end index. So if I is 0, the first chunk is going to start from 0, index 0, and all the items from 0 to chunk size are going to be the first chunk. And then for the second chunk, all the items starting from chunk size till chunk size into 2 are going to be the second chunk, and so on. Now we are going to find the minimum and the maximum value inside of this chunk. Math.min and const max equals to math dot max, spreading this array into individual values. So this math.max and math.min method accepts a variable number of arguments. So you can give it 1 argument, 2 argument, 3, and so on. So here we are just spreading this chunk array into individual values, into individual arguments, because this does not accept an array, it accepts individual values. And then it returns the minimum value from the provided arguments, and max method returns the maximum value from the provided arguments. Now that we have the min and the max values, let's just print it onto the console before we actually plot it onto the canvas. So here, as you can see, these are all of our values. And the range of these values is from +1 to -1. One thing to note here is that this PCM data, this channel data, has positive and negative values because it represents the waveform of an audio signal. So if you use the audio message feature in apps like WhatsApp, you'll notice that this is how your audio message looks like. There's a center line, there's an X axis, and then there's a Y axis. And then this PCM data goes above, has positive values, and then also has negative values. This is just how waves look like. Remember the sine and cos waves, they go up and then they go down. That's why there is a positive value and there's a negative value attached to each wave. Pulse code modulation data can have negative values because it represents the waveform of an audio signal which oscillates above and below a central axis, the zero line. This central axis corresponds to the equilibrium air pressure or the baseline level of the audio signal. Audio signals are waveforms that oscillate over time. The waveform represents changes in air pressure for analog audio or electrical voltage for electronic audio signals over time. When this waveform is digitalized through PCM, the values represent these oscillations with positive values indicating pressure above the baseline and negative values indicating pressure below the baseline. In typical audio waveform, the central axis or the zero line represents the point of no displacement or equilibrium. Positive values indicate displacement in one direction and negative values indicate displacement in the opposite direction. This is why PCM values range from a maximum positive value to a maximum negative value. So we are going to plot a bar graph such that there's a zero line and then the minimum value goes below that zero line and the maximum value goes above that zero line. Now to draw something on the canvas, we make use of this canvas context. So we are going to draw rectangles that represent different bars in the chart. Now, first of all, I am going to set the color, the fill color of the rectangles that we are going to draw. To do that, we are going to make use of the fill style property. Now, whatever I am going to draw using this canvas context will be filled with this provided color. And to draw a rectangle, we make use of the fillRect method. So it takes 4 arguments, the x and y coordinates. So these coordinates represent the top left corner of the rectangle, and then you have the width and the height. So this line of code draws a rectangle starting from the left corner of the canvas and draws a rectangle that has the same width and same height as the canvas itself. So it's going to cover the entire canvas with the blue color. It's going to draw a rectangle that covers the entire canvas. Let's test it out. So this is supposed to be canvas context and not canvas. As you can see, our entire canvas has this rectangle overlapping it. Let's check what the width and the height of our canvas is as well. Canvas dot width and canvas dot height. The width of our canvas is 300 pixels and the height is 150 pixels. But remember that we set the style of our canvas as width 100% and height 800 pixels. Then why is the height showing up as 150 pixels? And also the width is also inaccurate because the width of the canvas actually is 662 pixels. That's because when you set the styles using the width and the height property, that only sets the dimensions of the display size of the canvas. To set the width and height of the actual drawing buffer of the actual drawing canvas, you have to explicitly set the width and height either using these attributes or using JavaScript. So I'm going to set the canvas's width as 800 and canvas's height as 200. And let's remove this height property from here. So this will scale our canvas to fit the entire width of the screen. Now, as you can see, the width of the canvas is 100 and the height of the canvas is 200. And notice that I've also increased the number of chunks from 100 to 400. Now I can remove this rectangle. I don't want to fill the canvas with this color. Now, since we are going to draw these bars above and below a baseline, to determine that baseline, we first need to find the center of the canvas. Const center to canvas dot height by 2. And then let's also determine the width of the bars. So that will be canvas's width divided by the number of chunks. So that all of our data points actually fit our canvas's width. Now let's draw a bar for each of these min and max values. Right? The x-coordinate is going to be the index multiplied by the bar's width, and the y-coordinate is going to be the center minus the max value. So in order to move up from the center, we have to subtract a particular value. So here we are subtracting the max value, and then the width is going to be bar width. The height is going to be max plus math dot absolute value of min. So I just formatted my code for better readability. Let's see how it's working so far. So now you can see that we have a blue line here, but these are not the bars that we expected. That's because remember that our min and max values were between the ranges of -1 and 1. So very small values. So let's scale these values by a factor of 20 and see how these look like. So now our bars are taller and now we are able to see this waveform over here. So our audio is now represented as this bar chart that looks almost like a waveform, similar to this waveform that we saw before. But now the issue is that the entire audio is represented by this chart. But what we wanted was a moving graph. So this waveform represents the different amplitudes as the time passes. You can think of the x-axis as the time axis. Now as time increases or the time passes on, these are the amplitudes of the samples at that point of time. But what we want is as time is passing, we want a different bar chart for that time. But as of right now, at every point of time, we have just one value, which is the amplitude of the sample at that point of time. But we want a larger data set. We want more data so that we're able to plot a bar chart out of it. Right now, what we have is a static chart. What we want is a moving chart. Now, this is where fast Fourier transform or FFT comes in. Let's understand what FFT is. FFT stands for fast Fourier transform and it is a mathematical algorithm. So this algorithm helps us convert a complex signal like a piece of music from its original time-based format into a frequency-based format. So why is FFT important for audio? Any sound you hear is made up of multiple frequencies. For example, a musical note might include a fundamental frequency and several harmonics. So when you listen to a song is not made up of just one sound. At any point of time, there There might be multiple different sounds that make up that piece of music. And this is where FFT comes in. FFT helps us break down the sound into these individual frequencies. So right now what we have is the PCM data at any given point in time. We have a sample of that audio and the PCM method gave us the amplitude of that audio. But this FFT algorithm will help us give the different frequencies that make up that sound at that particular point of time. Now we can plot these different individual frequencies to create this visualization loop. By converting audio into frequency data, we can create visual representations like spectrograms or waveforms. This is useful for applications like audio editing software or music visualizers. Knowing the frequency components of a sound helps in various tasks like identifying notes in music, detecting specific sounds, or even removing noise. So you can break down a sound into multiple different frequencies, identify the frequencies that act as noise, and then filter those noise or those frequencies out. So how does this FFT algorithm work with audio? Think of an audio signal as a wavy line that shows the sound changes over time. This is called the time domain representation. So you can think of sound like this, like a wavy line that changes over time. So this is the time domain representation. FFT takes this wavy line and figures out all the different pitches, frequencies that make up the sound. This new way of looking at the sound is called frequency domain representation. So the FFT algorithm splits or breaks down this wave into multiple different waves representing the different frequencies. And this forms the frequency domain representation. After the conversion, we get data that tells us how much of each frequency is present in the sound at any given moment. So the FFT algorithm is a very complex algorithm, and frankly speaking, I will not even attempt to tell you the math behind it. If you're interested, you can check out these videos that do a wonderful job at explaining them. But here's a simple analogy that was given to me by ChatGPT that explains what's happening in a very simple language. Think of a complex sound as a smoothie made from various fruits or various frequencies. Normally, you can't see the individual fruits because they are blended together. FFT is like a magical filter that separates the smoothie back into its individual fruits. So you can see exactly what it's made up of. So right now we have this and we want this so that we can use this data, this frequency data to create a visualization effect. To get these frequencies, we need something known as an analyzer node. To create an analyzer, we make use of the audio context. Create analyzer. So audio context.create analyzer creates a new analyzer node, which we have stored in analyzer variable. So here inside of the visualize function, we don't really have access to the audio context. So we'll need to pass the audio context to this visualize function as well. Audio context. Previously, we used a random value 400 in our case as the number of chunks because we had 5 million different samples of data. So here again, we don't want the frequency analysis of all of these 500 million samples. Now again, when we are working with the analyzer, we need to divide our original samples into chunks. In order to do that, we make use of the FFT size property. So analyzer.FFT size. Now this cannot be a random value. The value of the FFT size must always be a power of 2 and should lie between the ranges of 32 and 16384. The default value is 2048. So here I'm going to set the FFT size to 256. Next, we have a frequency bin count property on the analyzer node. This frequency bin count is half of the value of the FFT size. So let's check that. So analyzer.frequency.bin count. As you can see here, the value of the frequency bin count is 128, which is half of 256. Now we are going to store the frequency data inside of this array here called frequency data. And we are going to use uint8 array, a typed array in this case. And the length of this array is going to be analyzer.frequency bin count. So the length of the data that is going to be returned is going to be exactly this length. Now the next step that we need to do is to connect our source, our audio file and the analyzer together so that when the music is playing, we get real-time frequency data. const source equals to audio context dot create buffer source. First, we need to create a source and then set the buffer of this source as our audio buffer, because this audio buffer contains the data associated with the audio file that was uploaded by the user. So we've created a source here and then set the buffer of that source to the audio buffer that was processed from our audio file. Next, we need to connect this with the analyzer. So our analyzer is over here. So let's move these lines of code below. We also need to connect the analyzer with audio context destination in order to actually play the audio. And next, we need to start playing the audio so that as the audio is playing, we get the real-time frequency data. Now, this is the array which is going to be updated in real time. And the method that we use to get the real-time data is analyzer dot get byte frequency data, and then provided this array. So this method is going to update this array with the real-time frequency data. Now we can remove this channel data logic and the chunks logic from here. Now here the number of chunks or the number of data points is going to be frequency data dot length. And frequency data dot length is also equal to analyzer dot frequency bin count. And again, number of chunks will be replaced by this. Let's store this value inside of a variable because we have used it twice. Let's call it length or frequency buffer length to be more clear. Here as well. And let's replace the last place. Now we don't need to create a chunk ourselves, and also we don't need the min and max value. Now our x coordinate is going to remain the same, I into bar width. The y coordinate will change here. It is now going to be canvas height minus the actual frequency data, bar width, and the height is going to be frequency data. Let's do one more thing. Let's print the frequency data to the console. Frequency data. Not inside of the loop, outside of the loop. Let's see if it's working. So I can hear the music playing. You probably cannot hear it because I have muted it while recording it. But I can hear the audio playing, but I don't see any graph being plotted. That's because you can see here the frequency data right now is 0. And there is also one more thing that is wrong here. We are only fetching the frequency data once. We want to get the frequency data at every interval. At, let's say our interval is 5 seconds, or let's say our interval is 1 second, for example. We want to fetch the frequency data at every second so that our frequency data array is updated, and then whenever this array is updated, we actually plot the bar graph. So every second a new bar graph will be plotted. So in order to do that, we can make use of the set interval function. And let's start with a 100 millisecond interval, and let's move this logic inside of our interval. We can move this logic outside of our interval callback function. Now, after every 100 milliseconds, analyzer dot get byte frequency data will be called, and this frequency data array will be updated. We'll log it to the console, and then we'll also draw it onto the canvas. Let's see how it's looking like now. Okay, you can see the different frequency arrays printed every 100 milliseconds, and you'll also notice this bar graph. But there's one major bug over here, that is every 100 milliseconds we are drawing a new bar graph, but that bar graph is overlapping the older one. So we need to clear our canvas first. Clear our canvas, we make use of the clear rect method. So this will clear the entire canvas, and only once the canvas is cleared, we are ready for drawing the next bar graph. Let's see how this looks like. Refresh. So now it's looking much better than before. We are able to see the different bar graphs being plotted after every 100 milliseconds. So now the visualization is looking better, but it's still quite janky. Let's reduce this interval to 50 milliseconds and see if that gives it a smoother appearance. So yeah, this is much better than before. Let me play the audio so that you can experience what I'm experiencing. So these are the different frequencies that make up that music at that particular point of time. Now we can make this bar graph even better using this function called request animation frame. So the request animation frame method takes a callback function. It tells the browser to call this specified function to update an animation before the next repaint. This method is designed to make animations smoother and more efficient, leveraging the browser's refresh rate to optimize performance. So every single time the browser repaints, we'll call this callback function. So instead of providing it a random interval, we'll let the browser decide when to call this function using the request animation frame function. Let's remove this console statement. So now the request animation frame will not call it before every repaint. It will only call it before the next repaint. So we want to call this function before the next repaint and then again call this request animation function from there. So this is a good example of recursion. Let's move this function into a separate function. Let's move this logic inside of this draw function. And then so let me explain what I just did here. So I moved the drawing logic inside of this draw function over here. And then I called this draw function for the first time. Now inside of this draw function, we call this request animation frame function, which will again call this draw function itself before the next repaint. Now in the next repaint, again, we call this function and again request animation frame again schedules this draw function before the next repaint. So thus forming a visualization loop. Let's see how it's looking like now. So now our animation appears to be much smoother than before. Let me do one more thing here. I'm going to increase the height of the canvas. So now that we have a basic logic in place, let's make this bar graph a little bit more pretty. I'm going to reduce the FFT size to 128 and I'm going to minus 1 from the width of this rectangle so that there's a certain spacing in between each of these bars. So it's already looking much better than before. If you can notice, these bar graphs actually look quite blurred. One of the reasons is because I am zoomed in quite a bit. And another reason is because I've set the width as 100%. So even though the actual width of the drawing space or the drawing buffer is 800 pixels, those 800 pixels actually are getting stretched to the 100% width of my screen. So I'm going to remove this for now. And my screen size is actually quite big. So let's see how 1000 pixels would look like. I've zoomed out as well. Now the resolution of my bar graph is so much better than before. I can do one more thing over here. I can add a gradient sort of effect onto these bars and maybe add a background color to the canvas itself. I'm also going to do one more thing. I'm going to set the width of the canvas to the width of the client itself and set the width here back to 100%. So now the actual drawing width and the canvas width both is 100% of my screen size here. Now I can increase the FFT size to 250 again. I'm just playing around with different values and seeing what looks better. I've also done one more thing over here. I have actually moved the canvas to the bottom of the screen using position absolute and bottom 0. Let's add a background to the canvas. Canvas context dot fill rect. I'm going to set it to this value over here. Okay, something went wrong in this context. Oh, that's because I'm clearing the canvas here. So I need to do this. So now I have a background on my canvas as well. I don't quite like this color, so I'm going to change this color to some other value. Yes, so this looks much better than before, but you can further improve it according to your own liking. Let's do one more final thing over here, which is add a gradient to these dancing bars. First, let's move this fill style inside of here. Let's convert it into an RGB value. So this is the corresponding RGB value, 82, 113, 9, 255, RGBA. And then we have this last argument for opacity. So let's make this opacity a bit more dynamic depending on the frequency data. So this is going to be frequency data I by 255. Let's use a template literal instead, just to make the string more readable. Let's see how this looks like. So we are going to stop at this point. Hopefully now you understand how to visualize a piece of music, what data to get, how to get that data, and how to draw onto the canvas. You can further look into the Canvas API to create different visualizations with the help of that frequency data. You can create different types of visualizations wherever your creative mind takes you. That's all for today. I will provide a link to the source code on GitHub in case you want to check it out. And if you take this project further and create more interesting visualizations out of it, I would love to see them. Feel free to share them with me either on Instagram or on Twitter. So if you like this project, you can find the full version of it and other such similar projects in my JavaScript mastery course using the link in the description box below. That's all for this video. I'll see you guys in the next one.